All right, let's get right into it. Today, we're going to tackle a really common question in statistics. How do you know if two separate groups are actually truly different from each other? Well, there's a fantastic tool for the job. It's called the independent t-test, and we're about to break down exactly how it works. So, let's paint a picture here. Imagine a company develops a brand new drug. They give it to one group of people and a simple placebo, a sugar pill, to another. Now, it looks like the drug group is getting better. But are they? Is that improvement real or is it just random luck? This is the exact kind of puzzle the t-test was built to solve.
When you boil it all down, the problem is pretty simple. We're just comparing the average results from two completely separate groups. It could be a treatment group versus a control group, or maybe test scores from psychology students versus math students. The point is, we need a reliable way to know if the differences we're seeing are the real deal.
To solve these kinds of mysteries, we need a sort of statistical detective. And the perfect tool for this tale of two groups is the independent samples t-test. It's designed specifically for this job. So, what is it exactly? Well, think of it as a statistical referee. It's a formal process that looks at the average, the mean, of two independent groups. And then it makes a call. It tells us whether the difference between them is statistically significant or if it's likely just due to random chance.
And here is the absolute best way to think about it. The difference in averages between your two groups, that's the signal. That's the interesting thing you're trying to find. But within each of those groups, there's always going to be some natural random variation, right? That's the noise. The t-test basically just asks one question. Is our signal loud enough to be heard clearly above all that background noise?
Now, it is absolutely crucial not to get this mixed up with its cousin, the paired t-test. As you can see here, our independent test, sometimes called the unpaired test, is for two completely separate groups. The paired test, on the other hand, is for when you measure the same group twice, like a patient's weight before and after a diet. Today, we are focused squarely on those separate, independent groups. Okay, so before we just jump in and start running our tests, we've got to do our prep work. Just like any good investigation, we need to establish our ground rules and our starting assumptions first. And this all starts by framing two competing stories. First, you've got the null hypothesis. You can think of this as the skeptical default position. Nothing interesting is happening here, the groups are the same. Then you have the alternative hypothesis. This is our exciting theory, the thing we're actually testing for, that there is a real difference. The t-test is going to help us decide which of these two worlds the evidence points to. Now, for our test to be reliable, we have to play by a few rules. The groups can't have any influence on each other, the data has to be numerical, not just categories, and ideally the data in both groups should have a similar spread and kind of follow that classic bell curve shape. If you break these rules, it's like using a broken tool. You just can't trust the results. All right, enough theory. Let's get our hands dirty. It's time to open up our case file and actually apply this t-test to a real-world example to see what happens. So here's our mystery. A professor wants to know if students perform differently on a statistics exam depending on whether they take it in the summer or in the winter. This is a classic tale of two groups. And here is our raw evidence. We've got the individual exam scores for the 13 students from the summer and the 11 from the winter. And yeah, just looking at a list of numbers like this, it's almost impossible to tell if there's a real pattern. So let's summarize this data to make it a bit clearer. The average score in the summer was about 52, while in the winter it was about 46. So, okay, there is a difference in our samples. But here's the million-dollar question. Is this difference big enough to be truly meaningful, or could it have just happened by chance? That's what the t-test will tell us. Now, right about here, you might be thinking about the complicated formulas behind all this. And the good news is, you don't have to worry about them. We let statistical software do all the heavy lifting and the number crunching. Our job is the really important part, interpreting what the results actually mean. So, the software has run the test, the calculations are all done. Now it's time to look at the evidence and finally deliver a verdict on our case file. And here it is. This is the single most important clue from our test, the p-value. In our case, it's 0.312. So what does that mean? Well, this number tells us the probability of seeing a difference this big just by pure random chance if there was no real effect. Think of it as the fluke factor. The most important step is to compare our p-value to a preset cutoff point, which is usually 0.05. Think of this as the line in the sand. If our p-value is below 0.05, we get to say the result is statistically significant. But our value, 0.312, is way, way above that line. It's not even close. Okay, let's look at a second piece of evidence to be sure, the confidence interval. This gives us a plausible range of values for the true difference between the two groups. For us, that range is from -6.3 up to +18.1. And here's the kicker. The rule is super simple. If this range of possibilities includes the number 0, it means that no difference at all is a perfectly reasonable outcome. Since our interval goes from a negative number to a positive number, it crosses right over 0. This confirms exactly what that high p-value was telling us. We can't be confident there's any real difference here. So, the verdict is in. Based on our evidence, we cannot reject the null hypothesis. We have to conclude there's no statistically significant difference in exam scores between the summer and winter. That small difference we saw in the averages, it was most likely just random noise. But getting the verdict isn't really the end of the story. It's just as important to understand the size of what we found, or didn't find, and how to communicate that clearly to everyone else. A p-value is great. It gives you a simple yes or no on significance. But we also need to know the effect size. This tells us about the magnitude of the difference. It answers the question, okay, so maybe there's a difference, but is it a big deal? A tiny trivial difference and a huge important one could both be statistically significant, and effect size helps us tell them apart. And finally, when you share your results, there's a standard way to do it so everything is crystal clear. You state the test you used, and you give the basic stats for each group. Then you report the key numbers from the test itself, the t-statistic, the degrees of freedom, that all-important p-value, and of course the effect size for practical importance. This gives everyone a complete picture of what you did and what you found. So, the independent t-test is an incredibly powerful tool. It gives us a clear, statistical verdict on whether two groups are different. But remember, that answer, knowing if there's a difference, that's just the first step. It really just opens the door to the much deeper and way more interesting question, why? And that is where the real journey of science and discovery begins.